Hi, welcome to the lecture on conditional probability. We are continuing our discussion on probability, and now we are narrowing it down to something called conditional probability. So let's look at some examples to better understand what conditional probability means. Okay, let's look at this first question. What is the probability that a card drawn from a standard deck of cards, that's 52, right, is a king? Now, we have seen this before, so the probability of drawing a king is 4 over 52, right? We know how to do this. This is the discrete probability definition that we talked about in previous lectures, right? Now, what is the probability that we draw a king given that we've already drawn a card from the deck and it is an ace? Now, we are given some additional information that obviously we did not have earlier, right? And now we have to utilize that in order to find the probability of drawing a king, right? In this particular problem, it's still easy because I can just go ahead and say that the 4 kings are still there in that deck. So it'll still be 4, but my sample space is going to be 51. Why? Because I've already drawn an ace and that shrunk my sample space to something else, right? This is the fundamental idea behind conditional probability. Because we are given some additional information, we can utilize that and update the information that we already had. Now, this helps us get closer to the actual probability of what we are interested in, which is my event in this case, right? So I already knew that something has happened or something has taken place, and then I updated my sample space and then found what the probability of that particular event is. Let's look at a more complex example, which is this one. Now we have around 5,000 students. Of those, 1,000 are CS students, 1,000 are math, 80 are dual, both math and CS, right? So what is the probability that a randomly picked math student is also a CS major? I would like to look at it in terms of a Venn diagram, right? Let me assume that this is my entire, like all of them, the 5,000 of them, right? And this is my CS, and here is my math, right? I know there is an overlap because of the dual majors, right? Okay, so if this question was framed something like this, what is the probability of a randomly picked student being a CS1? I would have easily said the probability of a CS major is 1,000 over 5,000. How? Because we know from our Laplace's definition of discrete probability, right? Similarly, if the question was framed like, what is the probability of a randomly picked student being a math major? I would have simply said 100 over 5,000 because that's my event, that's my sample space. We've talked about this before, so I'm not repeating that, right? Now, my question is, what is the probability that a randomly picked math student, so it's already known that the student is a math student, and I'm interested in the probability that this person is also a CS major. So now I'm writing something that is how we denote conditional probability, is that I'm trying to find the probability of a CS student given that that person is already a math student, right? Now I have that information here explicitly given to me, so I know that this is going to be 80 over 5,000. But if you really look at it, what we are doing here, and we go back and check our Venn diagram, I am trying to find this particular thing, right? But I'm also given that that person is a math student, right? So why am I even looking at all these like 5,000 students, right? I don't need to look into this entire space of these 5,000 people, because I already know that my sample space is going to be somewhere here, right? So that person could either be here or here, and so I have to find my event. Obviously is this, like the overlap, right? But obviously the entire probability or the sample space has to be calculated within my sample space, which is my shrunk space of math, right? So I would not calculate it like this, but rather I would say this is out of all the math students, because I already know that this person who was randomly picked is a math student, right? So that is what conditional probability talks about, to shrink the sample space up to that extent, which is what we are interested in, right? Let's look at it in a more formal. So in this scenario, my probability is 80 over 100, which is 0.8. Okay. Let's look at another example to better understand. But by the way, if you look at what we said here, to put it in better format or in a formula, and we'll see how this formula is derived, is that I'm actually taking the probability of CS intersection M over the probability of M, right? This is what I did here if you look at it, right? If I just put the probability of CS intersection M, that would be 80 over 5,000, right? So what I was taking earlier wasn't correct. And the probability of M, which is going to be 100 over 5,000, which eventually leads us to this, what we just saw. Okay, so then moving on to another example that shows us, and this is a bit string example I think we've done before as well. So let's look at it again in terms of conditional probability. A bit string of length 4 is generated at random. What is the probability that it contains at least 2 consecutive zeros? Again, as I've underlined already, given that the first bit is a 0. Right? So we have additional information that we must utilize and update the existing information, because as we saw in our student's example, this actually impacts the desired probability, right? So, which is why I'm saying when experiments are complicated, intuition may fail us, because it was easier in terms of when we were looking at the problem of cards earlier, but now this is not that easy. So we have to come up with a certain formula, with a certain technique, right? And so that's why we define conditional probability. Right, so the motivation behind conditional probability involves a two-step process. Step 1, restrict the sample space as we saw in the student's example, and then determine the favorable number given the new sample space. Right, and we know the formula: probability A given B. This is how we denote conditional probability, is nothing but probability of A and B where they intersect over total probability of B. Right? And that's stated here as well. E and F are events with the probability of F greater than 0. Obviously, we know that this exists, that this has happened, right? Then the conditional probability of E given F is denoted by probability of E given F and is defined like this, right? Let's look at the Venn diagram. Again, this goes back to our student example, but again, I'm repeating. This is how the equation comes into picture, because I could actually shrink my sample space. I don't have to look into this entire S, but I could just focus on this part, right? Okay, and then again, describing why, given that F has occurred, right? Let me just restrict there, right? Let me just go and look into there and then find the probability of E and F. So that's the idea which we just discussed, so I wouldn't repeat that. Let's look at this example to better understand. A bit string of length 4 is generated at random. What is the probability that it contains at least 2 consecutive zeros given, so we have some information already, given that the first bit is a 0, right? So let me have the sample space, the original sample space, which is set of length 4. So we know how many such bit strings are possible. 2 to the 4, sorry, right? Let E be the event that there are 2 consecutive zeros, right? 2 consecutive zeros, right? And F is the one, the given one, right? So first bit is 0. Okay, so what is the probability of F? I know that the first one is fixed, it's 0. And so the rest of them, for example, this is fixed. I still have 3 spaces to be filled in. That can be filled by 2 cube, which is 8, right? So this is 8 over, this is 16, right? So 8 over 16. Now, what is the probability of F and E, and why am I going to derive this? It's because that's the definition of conditional probability, right? I'm essentially interested in probability of E given F, right? So that's why I require this. Okay, so this is slightly tricky. We can go ahead and write down. I know that the first one is a fixed 0, right? Now, to have consecutive zeros, I can have a 0 here and anything here, either 1 or 0, right? So this is 4, 2 squared, right? I can have a 0 here and a 1 here, and just one more way of filling these, right? So one more. So there are 5 ways of having an intersection of f, which is first bit is a 0 and 2 consecutive zeros, right? So there are 4 of them out of a total of, oh sorry, there should be 5, right? Yeah. There are total 5 of them over 16. And so by definition, the probability of E given f is 5 over 16 by 1 over 2, because this is 1 over 2 obviously, right? And that gives us 5 over 8. Okay, so this was an example demonstrating conditional probability. Now we'll continue our discussion in the next video on conditional probability where we look at more examples.